Hi, I'm Ali Syed, Master of Science in Mechanical Engineering. Now I'm going to discuss a brief introduction about the nacelle structure and its design. To start with, first we'll see what is a nacelle structure and where it's exactly fixed in the aeroplane. Nacelle structure is nothing but a structure, a covering which will cover the engine of the aeroplane and the engine accessories and it also has thrust reversers employed on it. Actually, this is fixed under the wing in the commercial planes which we see these days, the Airbus, Boeing and all the planes. Whereas actually nacelle can be fixed under the wing, or else it can be incorporated within the plane, or else it can be above the wing as well, which is the recent study which is going on in the NASA, that they're trying to set up the nozzle above the wing. Well, but as we see most of the commercial planes, what we see these days, they are having their nozzle wing mounted. They are mounted under the wing with the help of the pylon. So we'll discuss everything about the wing mounted nozzles at the moment. Well, the whole engine is actually incorporated within the nozzle. It has the engine, it has the fuel system, it has the electrical systems, it has the thrust reversers, and it has the exhaust nozzle as well. Well, here is the line diagram of the exploded view of the nacelle structure. This is the inlet cowl. This is the very important part of the nacelle. This will decide how much is the mass flow rate the air will be coming in the nacelle, so that the engine fan can take inside. So this is the fan core. This is the middle body which will cover exactly the whole engine, and it has the NACA ducts on that. And this is the after body, which is a nacelle zone, which is a cover cowl. This will have and thrust reversers which are incorporated on that, which we'll further discuss about the thrust reversers when we go further into the detail. This whole structure is aerodynamically designed actually, because this is open for the air when the flight is on the TOC, which is the top of the climb, and there should not be too much of the drag on the surface, because of which will reduce the efficiency of the aeroplane. So this is actually connected with the pylon, and this pylon is fixed to the wing. This pylon is also structured aerodynamically. This will have inside fuel lines and electrical systems and all the accessories which this engine has been connected directly from the cockpit of the pilot. Thus everything comes to the pylon. So we have seen the exploded view of the nacelle structure. To understand the nacelle structure, we need to go through what all the parameters, what all the things which will affect the nacelle structure or its design, or why it is actually made, what all does it contain. To start up with, we'll see with what is a system, what all systems we have incorporated on the thrust reverser. First one is the control linkage. Control linkage is nothing but controlling the whole engine, because this engine is directly incorporated in the thrust reverser, which is totally fitted. So there are few linkages, there are few control systems within the nacelle structure, which will control the engine. So control linkage, not only to that, the linkage for the exhaust, the linkage for the thrust reversers to be deployed, all the control linkages are within the nacelle structure. The system contains firstly the control linkage, and it also contains the fuel system. As we know, but the whole engine has to be supplied, then it should be continuous fuel supply. So the fuel system is also employed into that, and the thrust reverser. Thrust reverser is actually planted at the end of the cowl, the whole nacelle structure, which is at the exhaust cowl. Thrust reversers are actually used to reduce the effect on the braking actually. When the plane is about to land, where it lands with a very high speed. So there are few moments where the main thing is to increase the efficiency. So to increase the efficiency, the plane should take less amount of time to come to its normal speed from the landing speed. So all the exhaust system which is from the engine or the nozzle, the exhaust which is coming from the nozzle from the engine will be high. So what this thrust reversal actually do is, it will block the exhaust system. Whatever exhaust is coming from the nozzle will be diverted. because of which there will be a huge drag, because of which there will be no thrust to the plane to move forward. It will totally take the 60% of the effect which actually a braking system of the aeroplane will have. So these thrust reversers are also incorporated on the nacelle structure. As like if you, when you're landing in the plane, suddenly you feel like you're moving back and you will see a bit of shockness on the aeroplane. That is because of the thrust reversers are deployed and they are an effect on the aeroplane. So these are the thrust reversers and the electrical system within that for the all the working of that, and the fire prevention. Even the design, the passages, the ducts, what we design within the nacelle structure should also design in such a way that if there is externally or internally, if there is a fire, that should not affect the other parts which are surrounding. So the whole nacelle structure has been designed in such a way that it will decide the path of the fire as well, so that it should not affect the engine if it is externally, or else even if the engine got burst, it should not affect externally. So that will be, the whole structure will be designed for that as well. And then we'll see what is a structure actually, what this structure should do, why the structure is really important, what all we need to do before deciding the structure. What is the engine burst, which I just explained. There is a one proper testing. What all the aeroplane engine companies do is a blade testing. They will break the blade and they will run the engine. They will let the blade to flow into the engine and they will see the whole engine will blow up. And they will see if there is any chances or any way the blown engine is coming out of its whole case. They will see if that is affecting its external parts. So that testing is done. That testing is done. So the structure is designed for that as well. That is nothing but the engine burst. So the structure should be designed in such a way that even the engine blows, it should not affect the external. Because what happens is, because if one engine blows, that will continually, if the fire blows up, that may affect the other engine. So for that reason, this whole structure is designed. And the foreign object problem, like any other object which is coming from the external ways, like when the flight is on the way or take off, like birds or anything. So even it's designed in such a way that anything which is coming, because of the huge drag, huge pressure, they won't be able to come within the near area of the nacelle structure which is having the engine. And the fuel volume, it should also have the fuel in that. And the weight is a really important thing, because like in the commercial planes what we see these days, which is carrying like Airbus A380, Boeing 747, all these planes are having a very high bypass ratio. Bypass ratio is nothing but the ratio of the amount of the mass flow rate in the inlet with respect to the amount actually the engine takes for this combustion. So most of the commercial planes are having very high bypass ratio. When the high bypass ratio increases, the size of the engine will increase. When the size of the engine will increase, the drag will increase. So as the size of the engine will automatically increase, that will increase the huge weight of the whole engine. So what is the main criteria when it has over here for such planes is that the nacelle structure should be designed in an optimum way. It should not gain more weight. It should not have more weight. So you should design in such a way that should be compact, that should be optimum, that should cover all the engine and its accessories and exhaust accessories in the whole part, and that should not actually be overweighted. So that is the one criteria which you need to see. And other is the axis. Axis is nothing but the structure should be designed in such a way. As you see over here, the fan cowl and the fan cowl, which is the main body of the nacelle structure, will open in such a way that will give an access to the engine. If there is any repair or if you want to replace the engine, if you want to do anything, the fan cowl will open. That is nothing but that is controlled hydraulically. So that is nothing but the access. The structure should have that access. So the system and the structure is designed. So now, as we see over here, this is the line nozzle. We'll discuss about the design of the nozzle as well over here. That is the main part of this presentation. We'll see what are all the parameters we need and what is the depth of the procedure we have to do to design the nacelle structure. So to go before that, to starting with the geometry and its aerodynamics design with that, we'll see what are the types of the nacelle what actually we have in the use. First one is the mixed nacelle, the other is a separate nacelle. Mixed nacelle is nothing but just this whole cover, whatever you see, that will cover the exhaust of the engine as well. It means the exhaust, whatever the engine is having, that will have the mixture of the a mixture of the exhaust gases because of the engine, and also the air which is bypassing over to the ducts over the engine will mix together and will have the exhaust. Usually this is used in the supersonic and the sonic aeroplanes because that will give a huge velocity, but the efficiency will decrease because of the mixture of that. Whereas here separate nozzle, the exhaust what you get because of the engine will go in one way, and the exhaust of the air which is bypassing through the ducts of the nozzle structure will go in the other way. So it is separate, that doesn't mix together. That is the separate nozzles, and all the commercial aeroplanes what we see these days will be having a separate nozzle, because if by this you can have a high bypass ratio, and that will not affect the engine nozzle, because if there is a high bypass ratio, there is a chances of having minimum pressure control, because the pressure has to be controlled at the end of the nozzle, which will affect if there is a high bypass ratio. For that reason, the separate nozzle is used. So now what we are going to discuss is about all the separate nozzle. So to start with design, what are the main things what are the dimensions you require? First one is you need the diameter of the inlet coil, the fan, and the exhaust nozzle, maximum diameter of the nozzle. You need the fineness ratio. Fineness ratio is nothing but the diameter of the nozzle, length of the nozzle to the diameter of the nozzle, and the ground clearance, intake geometry, and the lip section. We'll discuss about each and everything in further with formulas to see how we need to calculate over there. And the pylon, what you see over here, the length of from the wing, which is as it is mounted over the wing, we need to decide what is the length of the pylon as well. Usually the pylon is taken from like 50, it will have the length of the 50% to the 60% of the diameter of the fan, so that the aerodynamically whatever the air is going over through the nozzle, that should not have an interference effect with the aerodynamics effect of the wing. So that is a very important factor. Whatever the flow of the air over the structures of the aeroplane, that should not disturb the other one, which we'll discuss over here, that is aerodynamics. So this part will incorporate everything as I told earlier in engine everything. That is the internal part. The external part will play a more crucial role over here, because inside you can make an optimum design and you can incorporate everything safely. But the most important thing over here is having a proper aerodynamic shape of the whole nozzle structure, because that may lead to too much of the drag, that may lead to an interference, and that may lead to vibrations, and that may lead to an over noise. So this everything can be deducted, this everything can be minimized, this everything can be maintained within the limit what is required by the aerodynamic design of this nozzle structure. So aerodynamically we need to check about the drag, interference, surface roughness of the surface, noise, vibration, thrust, and the BPR level, which is nothing but bypass ratio level. So this is the aerodynamics of that. So now what we see is like, well, to start with the design of the nozzle structure, to make it easy, what I have done is I have divided this nozzle structure into three parts, which is the forebody, which is nothing but the inlet coil, and the mid body, which is nothing but the fan coil, and the after body, which is nothing but the exhaust nozzle of the nozzle, which will also have a thrust reversers on that. If the thrust reversers are not open, if they are not deployed, then the whole shape of the exhaust nozzle will have a direct aerodynamically shape. So that even when they are not in use, they should not have any drag, they should not have any effect on that. So for that reason, the incorporate of this is really important for that. As explained, now we'll see further about the forebody, mid body, and after body of the design of the nozzle structure. As design of the nozzle structure, first one is the forebody. As you can see, the first inlet coil, that is the forebody, and the main important diameter is what we need to find out over here is diameter of the throat. This will decide what is the mass flow rate should be going into the aeroplane, into the engine, and this is the highlighted diameter. This will be the tip of the diameter, this section, this circular section, the tip. This will decide. This is really helpful to increase the efficiency of the engine at the low speed characteristics. When the engine is going at the low speed, the engine will not have an improper mass flow rate, will not have a proper intake. So this actually the shape, the angle what we give over here decide the elliptical shape will actually drag the air into that because of that shape. If the air, even if the air is going from the other side, that will actually push into that because of that angle. So that is the highlighted diameter. and diameter of the fan, which will already come, which will come directly from the engine, you can calculate, and the maximum diameter of the nacelle structure. 4 baud is nothing but from the highlighted diameter to the maximum diameter. So to start with that, we first need to find out the throttle diameter and also the highlighted diameter. The highlighted diameter is estimated with respect to the throttle diameter by checking with the elliptical diagram, elliptical shape over here. But to calculate the throttle diameter, we need to find out what is the actual mass flow rate we need. Like, it is actually calculated to the extreme points. When the plane is at the high altitude to the top of the climb, we need to calculate what that is when it is more efficient, that more mass flow rate is required for the engine to maintain its thrust at that point. So for that reason, we need to calculate what is the mass flow rate at the top of the climb. So once we calculate the mass flow rate, we can estimate what should be the diameter, the throttle diameter of the fan. So to calculate the mass flow rate, the already proven formula for that is PTA by square root of TT, where the PT is nothing but the stagnation pressure and the stagnation temperature. Stagnation pressure and the temperature is nothing but, in the state of the aeroplane, the whole heat energy is the whole kinetic energy, the whole heat energy is converted into a kinetic energy. There will be, everything will be changed into the pressure, into the movement. So that the pressure and the temperature at that point is known as the stagnation temperature and the pressure. So PTA by square root of TT m square root of gamma is nothing but the ratio of the Cp by Cv, specific heat of the pressure and the volume, by R, which is the gas constant, and 1 by gamma minus 1 by m is the Mach number, square root of gamma plus 1 by 2 into 1 minus gamma. So this is the actual proven formula which we use to calculate the mass flow rate. We require the Mach number is, when it is at the top of the climb, we know what will be the highest Mach number. That will be decided with the engine itself. When the engine is being designed, actually, that will be designed for a certain Mach number. So we can take that extreme Mach number of the engine, and the stagnation is already done, and A is nothing but the area of the diameter of the fan, and gamma is the Cv by Cv. So we got all the values, and the stagnation pressure and the temperature can be calculated from this formula. For that is PT is P into 1 plus gamma minus 1 by m square power of gamma by gamma minus 1. Even the same way we can calculate the stagnation temperature. TT is equal to T into 1 minus gamma minus 1 by m square. So the Mach number over here, usually the subsonic planes, the commercial planes, what we see over here, usually the Mach number varies from 0.5 to 0.6. So for this calculation at the stagnation center, to decide with the throttle diameter, we take the Mach number as usually 0.6. Well, one thing which I want to clarify over here is in aerodynamics, all the diameters, like all the dimensions, are actually estimated. There is nothing which actually we can calculate and we can directly get the answer and we can go for that. Because with all the testings and with all the safety we need to mention, with all the aerodynamic structure we require and the inlet we need to require, actually the diameter or everything is estimated with respect to its approximate values. So even the similar way, once the mass flow rate is decided, we estimate the diameter of the throttle as well. So once we got the diameter of the throttle, we can actually find out by using the lip contraction ratio, which is nothing but the square of the ratio of highlighted diameter towards the throttle diameter. So this actually relation is used for calculating, for finding out the highlighted diameter. So we got the throttle diameter through the mass flow rate with respect to the required mass flow rate, which will mass flow rate will be decided with respect to the thrust the engine required for at the top of the climb. So it's actually a reverse process. We first decide the thrust, with respect to that we decide how much is the power of the engine should be, with respect to that we decide what should be the mass flow rate intake of the fan, and with respect to the mass flow rate we'll decide what is the diameter of the throttle. So that is as a reverse process. So once you got that, you will have the highlighted diameter as well. So this here you got the throttle diameter and the highlight diameter. Before going to that, I want to show actually a plotted graph for the diameter of the engine and the length of the engine with respect to the flight TW027. Actually they have plotted a graph, and then with respect by deciding its actual engine power to the 85. Here is SLS thrust. Here is the thrust which starts from 0 and go to the 1 lakh kilonewton, and here is the diameter of the engine. So by using this relation, y is equal to 1.0827 x to the power of 0.4134, which is nothing but, as it's already decided the engine, it's already tested on the engine which is having a diameter of the 85. They expected for the extreme positions what will be the thrust and what should be the diameter because of its variations what they were getting in the intake. So with that they plotted the graphs for the length of the engine and the diameter of the engine, as you can see over here. Similar way, if we know the thrust, this is how we actually estimate the throttle diameter. So as we got the mass flow rate, what we do is we estimate by using the formula as a throttle diameter, and then we plot the graph with respect to the thrust what actually the engine is giving, and from 0 to the certain point, and somewhere we have the thrust what actually the plane will be induced. So at that point we'll cross check, we can see what is the diameter of the engine. With respect to that we'll calculate what is the diameter of the throttle. So this graphs will help to find out the mass flow rate. This graphs will help to actually cross check the diameter of the engine, which will help to find the diameter of the throttle. So with this process of the forebody, in the forebody actually we find out all these things: throttle diameter, highlight, maximum dia, length of force body, shape of the inlet, internal external counter. So far we have calculated throttle dia and the highlight dia. To go with the next is maximum dia of the nacelle structure and the length of the forebody. The maximum dia is nothing but, as this is the structure of the nacelle, the top tip to the lower one is nothing but the maximum dia. So the maximum dia and the length of the forebody. For the calculation, as I earlier explained, in aerodynamics, in aerospace, all the components, the aerodynamic structure actually is calculated with respect to the estimation. For that thing, there is a ratio of highlighted diameter towards the maximum diameter, length of the forebody to the maximum diameter. This ratio is actually taken for the benefit of the efficiency, to reduce the actual flow rate, to increase the flow rate and to reduce the boundary layer of the nacelle structure, which is at the maximum diameter. This actually is taken by the author Ernest, who is working on the technical paper of that in the NASA. So as information taken from him, to find out the maximum diameter length of the forebody, we go with these two ratios. Because these two ratios are used to calculate the critical mass flow rate and the critical drag rise in the Mach number. What is the critical mass flow rate and what is the critical drag rise Mach number? Critical mass flow rate ratio is nothing but the extreme point, the point beyond which there will be the efficiency will decrease, the point beyond which there will be a spillage drag because there will be a excess air. So this critical mass flow rate is decided with respect to the DHL by TMX ratio and LF by TMX ratio, and MT is nothing but the drag rise Mach number. Even this is a limit. If the Mach number of the intake of the air goes beyond that, there will be a wave drag which will give a shockwaves onto the plane, which will increase the drag, which will make the whole plane imbalanced. So we have to maintain that mass flow rate should not cross the mass flow rate, critical mass flow rate, and the Mach number should not be less than the Mach number of the drag race Mach number. So this mass flow rate of critical, and this can be calculated, and this can be estimated once the design values are finalized, and by giving the values to this ratio, we plot a graph over here for the both ratios, DHL by Dmax and LF by Dmax. Here we plot the graph for the mass flow rate critical and drag rise Mach number, and then we'll see which is the estimated value, which will be the value which can give a proper efficiency, which can reduce the spillage drag and the wave drag, and a proper estimated level is taken further for the calculation. As I explained earlier, the relation between the critical mass flow rate and the MD, which is a drag rise Mach number, if the mass flow rate is less than critical mass flow rate, what happens? Here you see the graph. On the y-axis here you see is a CD, which is nothing but drag coefficient. What will be the effect of the drag on the aeroplane? On the x-axis you see the mass flow rate. So this is the point of the mass flow rate critical. The mass flow rate critical can be estimated from this point by taking, because when the engine comes, the engine has its capacity. The engine has its limit to the point which it can take the air inlet, beyond which because when the engine runs with high RPM, with a high bypass ratio, with a top speed, the mass flow rate required by that engine at the top speed at the high RPM is nothing but the mass flow rate critical. So that can be taken directly, but over here it is plotted for an understanding and it is plotted for an estimate value, because in aerodynamics, as explained, everything goes with estimation value. We have plotted for the MD and the MFR, which is nothing but mass flow rate critical. So I was explaining here that x-axis is the mass flow rate critical, y-axis is the drag coefficient. So if the mass flow rate, as you see the graph, if the mass flow rate is greater than the critical mass flow rate, the drag coefficient is normal. There is no any change in the drag coefficient. If the mass flow rate is less than the critical mass flow rate, as you see, the drag coefficient is increasing. Why? Why is it increasing? That will lead to a spillage drag. Spillage drag is nothing but excess air. If the air has went into the inlet, the engine has taken the air, but still there is an excess air left, which will cause a spillage drag. Because there is not enough mass flow rate for the engine to take everything. So at that point, that will cause a spillage drag. Similarly, if the Mach of the whole air which is coming is greater than the drag rise of the Mach number, what happens? As you see, similarly, at the x-axis we got the Mach number, and at the y-axis we got the drag coefficient. As the Mach number increases, there will be a wave drag, because the engine will maintain its own Mach number. If the air which is coming towards the aeroplane is having a higher Mach number, the intake air which is coming is going with higher Mach number, that will actually give a wave drag. That will actually lead to the shock waves in the engine. That will actually lead to the shock waves of the fan. So what we have to do is we have to maintain the inlet curve in such a way that can maintain the proper Mach number. That can control the Mach number of the inlet air. So for that reason, what we have to do is we have to maintain the Mach number always less than to the drag race Mach number, as you see over the graph. If the mass flow rate is less than to the required critical, that will lead to the spillage drag. If the Mach number is greater than to the drag race Mach number, that will lead to the wave drag. So with this mass flow rate critical in the MD, we will calculate over here. Once the point what we got over here, and we'll see what it is critical. With respect to that, we will estimate these ratios. In these ratios, we have already calculated the DHL, which is nothing but the highlighted diameter, and we have calculated LF, which is the length of the fourth body, which is usually taken about 0.7 times of the fan diameter. 0.7 times of the fan diameter, which we'll discuss later on further when we go with the internal contour. So we know the LF. So once you know that, it's easy that with this relation, once you get the design values of critical mass flow rate and the MD, you can calculate the maximum diameter of the nozzle. So in this, we have calculated the maximum diameter and the length of the forebody. Now we'll see the shape of the inlet lid. As I explained at the starting of the presentation, what is the importance of the shape of the inlet lid, as that will help to increase the efficiency at the lower characteristics of at the lower speed characteristics. This shape of the inlet lid, which is nothing but, as you can see over here, the tip of the shape, the curve, what you call the tip of the front tip of the nacelle is nothing but the inlet lid. Usually that is taken in an elliptical shape, or for a sonic jets and everything, it is taken as a super eclipse. Over here, as we are discussing all about the commercial planes and the subsonic aeroplanes, it is taken as an elliptical shape. So to start with that, as we know the standard formula for the canonical form, where the major axis is greater to the minor axis, we go with the formula x by a whole square plus y by b whole square is equal to 1. So in this formula, we got the A is nothing but the major axis, B is nothing but the minor axis. This major axis and minor axis is nothing but, as this is the tip of the nacelle and this is the elliptical shape, here it will take the, what we require is only the quarter, 30 to 40% of that elliptical, not, it doesn't take a whole elliptical shape actually. We just take the quarter of the elliptical shape and that will be incorporated at the tip of that. So here you got this. This is the elliptical shape, this is the major axis and this is the minor axis. So this is A and this is B. So we can calculate the B actually, but what will be the A? So what will the A will be the major axis. The B we can calculate in such a way, the B is nothing but the length from the throttle diameter to the highlight diameter, the difference between that, which can be calculated by the difference between the highlight diameter to the throttle diameter divided by 2, which will give the actual minor axis. But major axis is actually considered because with the research actually done by the Albert and the Miller in the technical paper of the NASA as well, they have decided the major axis should be 2 times to the minor axis, and the exponential what we are having is x by a is whole power n, that n is directly taken as a 2. So if we increase the take the value as a is equal to 2b, which is nothing but major axis is 2 times the minor axis, and with the exponential form of 2 in the elliptical in the eclipse formula, that will increase the efficiency, that will increase the inlet of the air. This is already a research work which has been proven in the NASA. So from that time, usually for most of the calculations of the shape of the inlet lip, they actually take the value as 2. So even here we have considered this axis ratio and the exponent as a 2, and we have incorporated that formula. And as we know the B, the value of the B, we will get an equation. Well, that equation is x square by it's 4b square plus y square by b square is equal to 1. We know the value of the B. Well, that will give an equation of the eclipse. That will give an equation of the eclipse. So with that equation of the eclipse, with the values of the x and the y, with the point, we can plot an eclipse. So we have to see which part of the eclipse is actually the shape of the inlet tip. So what we do is over the here we draw the axle tip, we draw the origin x-axis and the y-axis, and then we take the whole coordinate system over here and see what will be the x and the y points from that point. It's nothing but the center, like we take the tip of the throat diameter, we take the tip of the highlighted diameter, we draw a horizontal lines and we'll see whatever the point that is considered as the origin. From there we will take the x and the y values and then we'll draw an eclipse, and whatever the part which is covering the tip of the highlight diameter to the tip of the throat diameter will give an eclipse shape. So that will be the final shape of the inlet lip. That shape is really important because, as I explained, that will decide what should be the mass flow rate actually going into the plane, and that will decide actually at the lower speed characteristics that will increase the efficiency. So, and then we'll go with the internal contour. Internal contour is nothing but the internal part of the forebody, which is nothing but from the throat diameter to the fan diameter. What should be its shape and what should be its length actually? Actually, this is a diffuser. This will be a diffuser duct because as over here through the throttle diameter, the whole intake air will go in. That has to spread all over the fan. So for that thing, we use a diffuser duct. And usually there is a diffuser ratio, which is nothing but the area of the fan to the area of the throttle. So this ratio is actually maintained at 1.25 up to the 1.35. There are many ways to estimate. As I explained, the throttle diameter is already calculated earlier. So this point is also taken into consideration for the estimation. As I told, everything is calculated with an estimation process. We can use this ratio as well over there to check if the throttle diameter what we have is within the limit. And this is also proven by the research that the area of the fan and the area of the throttle diameter of the nozzle should range between 1.25 to 1.35 for the better results, for the better efficiency. So with that thing we'll have the diffuser ratio. With that thing we can actually see what should be the actual curvature or actual circular length inside. And the length of the internal part of the globe is taken as 0.62, which is the minimum, which is actually the minimum value we need to maintain for the smooth flow. That is the minimum value. 0.62 times of the fan diameter is the length you need to maintain to minimize the noise, to give the intake air a proper flow. So that is the minimum value. So you can take beyond that as well. But as per the research in the survey, literature survey, what I have done so far, this is the point what I have got is length should be 0.62 of df. So here we got the internal contour as well. So far we have gone through the design of the forebody. Like we have decided the throat diameter, highlight diameter, and we have decided the shape of the inlet lip. We have decided the maximum diameter and the length of the forebody, and also the internal curve, which is a diffuser ratio and the length of the internal of the forebody. So as we completed the forebody, now we'll go to the afterbody, because the mid body is nothing but is actually a circular shape which will be joining the afterbody and the afterbody and the forebody. So that can be directly taken as from the maximum to the maximum, because that will not have any difference in its diameter, so that can be taken. Whereas in the afterbody, why is afterbody important is because here we need to decide the diameter of the nozzle, like exit nozzle of the nasal structure, because in the mixed nasal structures, this diameter of the nozzle will incorporate the engine nozzle, that will cover the engine nozzle, that will have a convergent shape as well. So that will also help for the exhaust gases to take its path. That will also have an effect to increase the thrust and to increase the efficiency. So here afterbody design, this is the diameter of the maximum diameter, this is the diameter of the nozzle, this is the length of the afterbody. The curve, the circular curve what we are having over here, this is very important as well, because as we see in the nasal structure, as aerodynamically the air is flown over here, and this part will have an effect of this air. If this circular ratio is less, this will have a shape of this, which will separate the flow. For example, like as we see, as we got the hand over here, and this is the structure of the nasal structure. If you blow air from here, you will feel the air at all over body, all over the hand. If you increase this RA, and then if you blow the air, you cannot feel the air at this tip of the nasal structure. That will have a separate flow because of the wind which is coming beyond, which is coming from the other ways, or which can be an interference effect from the wind. So that will increase the drag. That will not give a profile drag what actually is our target to require. So we have to maintain the RA. What happens if we give too much of the RA? Too much of the will increase the whole radius and then radius and the angle. Because of that, the boundary layer will increase. If the boundary layer will increase, it will be nothing but a flat surface, because of which there will be increase in the drag as well. So we have to maintain the RA and we have to maintain the beta, which is nothing but the chord angle. So how to decide that? So to decide that, we have a relation RA by maximum diameter, which is equal to 0.04 by 1 minus MD square, which is MD is nothing but the drag raised Mach number. So here we got the relation. This part is the same what I explained just now. If this ratio is small, the boundary layer grows, which will separate the flow. If it is too high, it's a skin friction drag, which will increase the drag as well. So this RA and beta, that has to be decided. So we have a formula over here, is tan beta C is equal to D max minus Tm by 2LA, which is nothing but directly taken from this part over here. This beta is nothing but half of the angle beta. So usually the beta value will be less than or equal to 16 degrees approximately. That won't be beyond that, because of the actual research work which are done by the scientists. They have decided that will be approximately equal to the 16. So the beta C should be half of that. So D max we know that, and dn is nothing but the nozzle diameter. This can be estimated once we got the engine, and once that covers the engine, that can be actually estimated with respect to the what should be the exhaust gases, at what speed they have to go and what pressure they have to go. So once we got that things, we can decide the diameter of the nozzle as well. So once that is decided, and the L is nothing but the length of that, and then you can calculate the beta C. So once you got the beta C, the twice of that is nothing but the beta. So once you got the angle, this can be made, the arc can be maintained from the maximum diameter point to the diameter of the nozzle. So this is a process by which it's estimated for the design values. This process will be best for the shape and the angle, which will reduce the drag, which will give a proper shape and which will increase the efficiency. So here we got the design of the after body. So here so far we have seen the main parameters, the main design structures, the external design structures of the nacelle. The internal are very typical with respect to the design, because like there are too many parameters which will come, like engine, fuel systems, electrically. So internally totally varies. So whatever we have designed over here is the external part of the nozzle structure, from throttle diameter to the exit diameter of the nozzle. So far we got a view how to design, and we got a proper design of the nozzle structure. Now we'll see to the design what we have designed for the so far. Now we'll see for the design of nacelle structure what we got over here is giving a proper drag. Is if the drag what is we are having because of it is within the limits. So to see that, we have a proper formula to calculate the drag. Before that, we'll see how is actually the drag coefficient, how is actually the drag will affect on that. So this is the nozzle structure, and this is the air which is blowing towards the nozzle, and you see the flow of the air. The flow of the air should take the flow of the profile of the nozzle structure. That is the perfect drag. If the profile is not right, the possible nacelle drag, the drag because of the nacelle, usually will have only profile drag. If there is any imbalance, uncertainty in the design, that will have a spillage drag, that will have a wave drag. So what we have to do over here, we have to maintain the mass flow rate, that should be within the limits of critical mass flow rate. We have to maintain the Mach number, that should be within the limit to the rise in the drag rise Mach number. If they are within the limits, if they can be maintained, then the drag what you will get on the nacelle structure will be a profile drag. That will balance it. That will not give any shock waves, that will not give any vibrations, that will not give any external shock waves or vibrations on the engine. So in the whole nacelle. So for that thing, what we have to do over here is we have to maintain this everything. So if MFR and MO is within the limits, then it is a profile drag. If it is not within the limits, then you will have all the drags, profile drag, spillage drag, and the wave drag. So we have to maintain the mass flow rate and the Mach design number. So here you got the formula to calculate the actual drag of the nacelle structure. So in the nacelle structure, formula is half rho V square, the maximum area into the discharge coefficient. So here we know the rho, and we know the velocity, we know the maximum area of the nozzle, and CD is a drag coefficient, which can be calculated using this formula, that is 1 plus 1 by 3 into 1 minus DHL by D max by LF by D max, that is 1 plus 7 by 4, 1 minus MFR, maximum flow rate, into maximum area by maximum highlight area minus 1. So in this formula, we know all the values of highlighted diameter, maximum diameter, and the length of the forebody and the mass flow rate. We can calculate the discharge coefficient, in which you got the CF, which is nothing but a skin friction coefficient, which can be calculated by using the Mach number and the Reynolds number. So you'll get the drag coefficient CD over here, and then you can calculate the drag. So this drag is the actual drag which is having because of the nacelle structure. So similar formula is used as over here. The formula what explained over here is for the forebody nacelle structure. The similar formula can be used for the afterbody nacelle structure as well, by changing the values of the highlighted diameter to the nozzle diameter. So and then you can calculate the drag what is actually affecting on the nozzle. nacelle, and that can be compared with the actual thrust, because the thrust should be, the drag what you're having on the aeroplane should be equal to the thrust what you're getting because of the aeroplane. That should not be over to that. If the drag is huge than the thrust, then the efficiency will decrease. If the drag is too high, that will go to the ultimate speeds. So we have to maintain that the drag should not be much beyond that. So that is the actual check what you do with the drag. So this is the brief thing about the nacelle drag coefficient. So far we have seen the design, we have seen the calculation of the nacelle drag coefficient. Now, once the design is done, we calculate the dimensions, we got the dimensions. Now the important thing over here is geometrical dimensioning and tolerance, which is GD and T. So this geometrical dimension and tolerances is nothing but a symbolic representation which will be useful for the engineers. It's a communication, it's a mechanical communication. It's just a representation which will easily, the design will communicate with engineers or manufacturers or designers or quality. They can directly interpret the whole design. So that is the whole design actually. So once we got the dimensions, we'll give it as a representation. Here we got the sample, like throat diameter, that is circular. 75 is its nominal value, plus or minus 0.09. What is sample given over here is the tolerance, its upper limit and the lower limit of that. So here we got the nacelle, we can see like we have given a shape representation for the GD and T. The values are not mentioned over here as we have not done any calculations. So throat diameter, maximum diameter, highlight diameter is the circular, and the beta, the chord angle, which is expected angle, and the RA is the arc which is maintained at the after body, and the surface finish of the nacelle structure is also mentioned with this with the symbol. So this is actually a presentation which we do for the geometrical dimension and the tolerance. So once the dimensions and the tolerances of each part is actually finalized, is actually decided with respect to the fit it is having with the other component. So the fits it is having will decide what is the tolerance. By using the standard charts what we got in the industries, we'll decide what will be its upper limit and the lower limit. So dimensions and the tolerance are decided. So once it's decided, we have to see if the assembly tolerance is within the limits. As we see, the nacelle has too many parts, too many components. Each component has its own tolerance. Each component can be within its upper limit to the lower limit. So once that everything is combined, once that everything is joined, the whole tolerance of the assembly should be within the limits. It should not exceed. So that process for checking of that assembly tolerance process is nothing but a stack-up analysis. This is used to control the critical assembly. This is used to check if the critical assembly is going critical or not. That will tell the variation of the assembly, and as if the variation is more, if there is a variation in the assembly tolerance or assembly, then we'll see which parts has to be rejected or which parts has to be changed because of the duration, and then we'll see if that has to be changed at the design or if that is a problem of the manufacturer. So at the production. So this process will help to see where the problem is, if it is in the design or in the production. So that is done. So the quality or analysis check is done to see if the assembly tolerances is within the limit or not. So how we calculate the assembly tolerance theoretically? There is a formula with respect to the standard deviation for the measured model of the stack-up analysis. Square of the standard deviation of the assembly is equal to the sum of the square of the standard deviations of each component. Here standard deviation is taken with respect to the process capability of 6 sigma. That is, each component is equal to total tolerance divided by 6. We will get the standard deviation of the component. As here you can see minus 3 sigma plus 3 sigma. This is the nominal diameter which is at 0. Upper limit, lower limit. We will sum these two. For example, it is plus or minus 0.1. The total tolerance will be 0.1 plus 0.1, which is 0.2 divided by 6. We will give the standard deviation of the component. So we will substitute that, and then we will get the standard deviation of the assembly. How will you check if that is the nominal, if that is reliable or not? So once you got the standard deviation of the assembly, you will multiply it with 6 and divide by 2 to get the actual limit of the tolerance, that plus or minus. It is just a reverse process from here. So once you got that, you will check that with the actual assembly tolerance. So if the assembly tolerance is less than or equal to actual assembly tolerance, then the design is reliable. The assembly tolerance should not be greater than the actual tolerance. Actual tolerance is nothing but sum of all the upper limits of the tolerances. So we have to see if this design tolerance is coming within the limit less than or equal to the actual assembly tolerance. If it is, then the design is reliable. So this is a stack-up analysis which is actually process done to check with the assembly once the whole each components of the nacelle is done, to check if that is having a proper structure, because we need to maintain the freights, we need to maintain all the dimensions for the thrust reversers or connecting of the inlet coil, fan coil and the exhaust coil. So once that is done, final what we do is a design check. Design check is nothing but a review of scheme design focus on design standards, quality and the material type. It is nothing but focusing on if the whole design process has gone as it has to be from the inception to the construction, which is nothing but from the scratch design, from the concept design to the construction. If it has followed its standards, if it has followed the requirements, industry requirements, that nothing but customer needs, if it has followed the quality. So it's actually a design check report is maintained in the industry, which will have the about detail about each and every component, which will check that, which will see if it, which will validate if it has followed the design requirement, and then if that is validated, then design check clearance is done and design clearance report is given. So this is the final point for that design check. So now so far we have seen nacelle, design of the nacelle, design of the inlet nozzle, fan coil and the exhaust, and then we have seen the geometric dimensional tolerance theory and T, stack-up analysis and the design check. This is the brief description about the design of the nacelle structure. Hope this has given you a brief idea. Few points of this has been taken from the knowledge what I gained in my masters in mechanical engineering from UK, stack-up analysis and GD&T, and this everything generally in aerospace this is used for the designing is used in the CATIA. So I also have a diploma in CATIA 3D modeling. So this is a whole process or linkage of the design of the nacelle structure. Thank you.